So limits of infinity. What does that mean? What this is, a limit of infinity, is if you're taking a limit as x approaches infinity of f of x. That's what a limit of infinity means. Or you could take the limit as x approaches negative infinity of f of x. These are limits of infinity. They're limits going forever in the positive x direction, forever in the positive x direction, or you're going forever in the negative x direction. Limit going towards infinity in the positive x direction or negative x direction. Positive x direction or negative x direction. What this looks like graphically, a limit of infinity, is if you're going towards positive infinity, right? Let's take a look at let's see, a graph that looks like, oops, like this. No, you're supposed to have, there we go. Let's look at our asymptotes. Graph looks like this. Negative infinity will be green. Positive infinity is in this direction. So if you're approaching positive infinity, you're wondering, what is the graph doing? What is the function doing? This is f of x. This is f of x. What is the function doing as the x value gets bigger and bigger forever towards infinity? You're wondering, what is the graph doing? What number is f of x approaching as x goes to positive infinity? So x gets bigger. That's the question. What number is the function approaching as x gets bigger, as it goes towards positive infinity? And so for our value, we see x is getting here, right? It's going closer and closer. What we have is this dotted line that is a horizontal asymptote. Horizontal asymptote. And when you look towards infinity, that is where the graph, that is what f of x approaches as x gets bigger and bigger. This horizontal asymptote is skimming along, right? As you're getting further and further to the right, the graph is approaching this horizontal asymptote of x equals some number, we'll call it, well, in this case x is 0. So from the graph, the limit as x approaches infinity. Let me do a better infinity symbol of f of x equals 0. And this is the horizontal asymptote of the graph. Asymptote. That is what limits of infinity find. Limits of infinity find, they tell you where the horizontal asymptote is of your function. Similar, as we approach negative infinity, right? We ask, what is f of x approaching? This direction is negative infinity as x gets smaller. More and more negative, I should say. Because it's a very large negative number. So positive infinity, negative infinity, right? And again from the graph, the limit as x approaches negative infinity of f of x equals 0 in this direction. So this is your horizontal asymptote. This defines where the horizontal asymptote is of a function. These horizontal asymptotes, right? We know about vertical asymptotes. Vertical asymptotes are points of discontinuity. Horizontal asymptotes are not points of discontinuity necessarily. They're just a kind of what's happening at the ends of the graph. Horizontal asymptotes care about what's happening on the ends of the graphs. So as we're going towards infinity, right, we want to know the edges. We want to know the edge behavior, the end behavior of these graphs. What is happening on the extremes? What's happening on the extremes? We don't really care what's happening in the middle. The limit of infinity doesn't care what's happening in the middle of the graph. It can be going up and down, wiggling side to side, doesn't matter. The middle of the graph doesn't matter. Infinity only cares about the edges of the graph. Limits of infinity only care about what's happening on the ends. So, infinite limits or limits towards infinity only care about the end behavior it's an R of a function at positive infinity and at negative infinity. In infinite limits, limits towards infinity only care about the end behavior of a graph. Where is it going? What's happening to your function? What's happening to your function on the extremes? On the extreme far left, the extreme far right, what's happening in those positive, negative infinity sections? The end behavior of the graph. Don't care what's happening in the middle. Middle, that's for other limits. Limits approaching 2 or 7 or whatever. End behavior of infinity, we care about big, big numbers or big, big negative numbers. Yell at me if you need me to stay up here. I'm going to scroll down a little bit. So since we only care about end behavior, we need to kind of think about what's happening in these functions. We need to, again, in AP Calc, in these limit situations, it's very important to be able to understand the equation from multiple perspectives. Be able to hold it in your hands and turn it and see it from different directions, like a graph or a function when you plug in numbers, or a table. Different kinds of, or simplifying it, you can do different things to these equations, right? You need to be able to see it from all different angles. So if we do, for example, find the limit as x approaches infinity of the function x. Now, let's make it a little bit more complicated. 2x plus 1. Find the limit as x approaches infinity of 2x plus 1. What is this function? What is 2x plus 1, the graph of 2x plus 1, right? We need to be able to understand these equations, what they look like, what kind of equations they are. We need to know what this equation looks like on its end behavior. We care about the end behavior of this graph. So what is the end behavior? What does this graph, what does 2x plus 1 do as you get bigger and bigger? What does it look like? Well, if we look at the graph, 2x plus 1, we know this is a linear equation. We know this is a line. Right? 2x plus 1, we know this is a line. And so a linear equation is going to look something like this. This is the graph 2x plus 1. As x approaches infinity, as we get bigger and bigger, what's happening to the function? Where is it going? What's it doing? As we approach infinity, as we get bigger and bigger in this direction, this graph is going up, and it's going to keep going up, and it's going to keep going up, and it's going to keep going up forever, right? Keep going up forever. So as this function approaches infinity, is there a horizontal asymptote? Is there a particular number we're reaching? Is there a particular spot that this graph is going to kind of like get close to? Not really. It's going to go forever. So the limit of infinity, if we keep going, it's going to get to infinity. And that's our answer, right? This function, the end behavior of this graph, goes forever. So the limit as x approaches infinity, well, since it's going to keep going forever, it's going to be infinity. It's going to reach infinity. It's going to get to the positive infinity side, going forever. What about the limit as x approaches negative infinity of 2x plus 1? Where's that going? So this was the limit as x approaches infinity. What's the graph going to be as it approaches negative infinity? Limit as this function, 2x plus 1, approaches negative infinity. Now we're going to the left side. Now we're going towards negative infinity. This is the end behavior, right? Limit as x approaches negative infinity. Well, we're going forever downward. So yeah, we're going to be negative infinity. We're approaching, right, that end behavior of the function is going down forever. And this is what we mean, the end behavior. What is happening on the edges of the graph? Is it going up? Is it going down? Or is it approaching some horizontal asymptote? What is the end behavior of this function? So limits of infinity look at the end behavior. Let's look at another example. Find the limit as x approaches infinity of negative x squared. Negative x squared. What is happening with this function as we get to the end behavior of this function? Look at the end behavior. Does anybody remember what negative x squared looks like? Can you shape it with your hands? Show me with your hands, or someone have a picture? What's x squared? All x squared equations, what do they look like? Yeah, Paris, you got it. It's a parabola. X squared is a parabola, right? Parabola, since it's negative parabola, that means that this is going to be like this. Negative x squared, right? That means it's a downward facing parabola because it's negative. So then, well, we look at our infinities, right? What is the approaching the positive infinity side? What's the graph doing? Going down forever, right? So here is the limit, limit as x approaches infinity. We're going towards negative infinity. The graph is going down. Down is the end behavior. End behavior is going towards negative infinity. Same thing as the limit as x approaches negative infinity of negative x squared. We can look at the negative end behavior. This side, also this side. Limit as x is negative infinity. Also this side, going towards negative infinity, going down. So we're looking at these end behaviors of the graph, figuring this whole thing out. Where's it going? Okay. So, looking at these equations, looking at these graphs, they help us, the graphs help us to identify the end behavior of the function. Being able to picture the graph is a very helpful way to realize sort of what's going on with the function and get the situation. But we have sometimes complicated looking equations. How can we tell from these complicated looking equations, if the equation is much more complicated, is there a little trick we can do to find out what the end behavior is going to be like? If we can tell if it's going up or down forever, is it going to be positive, negative, infinity? How do I know with a much more complicated looking equation? And there's a nice little trick you can do. Let me show you the trick for each of these equations, right? A trick you can do. You can plug in, I'm going to put plug in quotes, infinity or negative infinity. We're going to imagine infinity like a number, and we're going to plug it in to these equations. And when we plug it in, we can kind of use it like a variable, cancel stuff, do some math to it. As long as we understand what we're doing, we can plug it in, and that'll give us our answer. So if I, for example, took the limit as x approached infinity of 2x plus 1, the same function we had before, 2x plus 1. If I plug in infinity, it's going to be 2 times infinity plus 1. Well, infinity is like the biggest number ever. So if I add 1 to it, does this 1 really like matter? This 1 doesn't really change it. Infinity plus 1. Oh, like, sure. Doesn't change the number. It's still infinity, right? If I multiply infinity by 2, does that change the number? It's still infinity. It's still a really big number. Infinity times 2 is still going to be friggin' infinity. So no matter what I do, right, 2 times infinity plus 1, all of those are positive. All of those are big numbers. The infinity is the thing that's going to stand out. The infinity is the thing that's going to really, like, keep it together. So this is just going to be infinity. Oh god, that's a really bad looking infinity. Hold on a moment. There we go. Right? 2 times infinity is still infinity. That's what I want to say here, right? 2 times infinity is still infinity. 2 times infinity is still infinity. So we can like imagine plugging it in, and we say, well, what happens to this infinity? Does it still remain positive? Is it negative? What's happening? Same thing with the limit as x approaches negative infinity of 2x plus 1. I'm going to plug in 2 times negative infinity, right, plus 1. So I'm going to have now, I have a really big negative number, the biggest negative number, negative infinity. If I multiply negative infinity by 2, 2 times negative infinity is still negative infinity. It's still a negative number, right? Doesn't matter, I multiply 2. Well, so the reason I crossed out the 1 is that let me show you here. If I have negative infinity plus 1, is that going to change the number? Is that going to make it into a positive number? Right? That 1 is like insignificant. That's why I crossed it out, because it doesn't matter. All right, insignificant. Insignificant. If I have a negative infinity and I add a 1, it's not going to change it, right? It's not going to change the number. It doesn't matter, right? The positive 1 also insignificant, too small to matter. Negative infinity plus 1, it's still going to be negative infinity. Right? So we kind of we're tracking this negative number, this negative infinity or the positive infinity that we plug in. You're kind of imagining plugging in infinity and seeing what happens to it. Adding, subtracting numbers don't matter. Multiplying, maybe if it changes signs, if it's positive or negative. But a number times infinity is still going to be infinity, right? It's not really going to change our value. But if I add 1, infinity plus 1, what's that going to be? It's not going to matter. It's too insignificant to influence our result. It's still going to be negative infinity. We can do the same thing with this negative x squared. If I do the limit as x approaches infinity of negative x squared, if I imagine plugging in infinity, I'm going to get negative infinity squared. So what's negative infinity squared? Well, infinity squared is still infinity. Well, you're on the right track because of the squared, right? And the negative and the squared. The problem is this order of operations, PEMDAS, we do the squared part first. And once we square it, we get a positive. And then we do negative times infinity is going to be negative infinity. And remember, that was our answer we got, right? This negative infinity. this negative infinity over here. The reason why it's negative infinity is because this negative in the front makes this infinity into a negative infinity, right? Makes the problem negative. So it's going to be negative infinity because that negative in the front, this negative in the front here, changes the sign of our infinity. Negative infinity changes the sign. Because you're multiplying negative times infinity. This is a negative infinity here. Negative infinity. It's like you're multiplying by -1. Multiplying by a negative changes the sign, changes the direction of your infinity. And so we're going down towards negative infinity because we had that negative in front. Same thing if we plug in negative infinity. X is approaching negative infinity of negative x squared. We're going to get negative infinity squared. Okay, so we've got this negative infinity squared. What is negative infinity squared? What happens when you multiply a negative times a negative? Yeah, exactly. Positive infinity, that's it. Becomes a positive. Because you squared the negative. Becomes positive. I'm running out of room here. Yeah, negative times a negative infinity times a negative infinity, multiplies, becomes a positive. Negative times a negative is a positive. So when you squared it, became positive. But then again, we also now have this negative in front. So I have a negative times something that became a positive. Negative times a positive, that's going to become another negative. Got negative times infinity. That looks like a pretzel. There we go, better. Is going to equal negative infinity. So because of this negative sign in front, again, changes the sign to be negative infinity. So you're dealing with infinities, but you're really just dealing with, is it positive or negative? Really what you're dealing with is the infinity a positive infinity? After doing all the math, after looking at the symbols, if I squared something, or if I cube something, right? Cubed stays negative, right? Negative infinity cubed is going to stay negative. Am I multiplying it by a negative? Which direction am I going to end up going? Am I going to go positive infinity, or am I going to go negative infinity? So look at your multiplication, look at your symbols. Think about what happens if I plug in infinity to the situation. What's going to end up? What is that number going to end up becoming? Okay. Questions about that? Okay. So a couple other things. So we now can figure out if it's infinity. We can figure out if it's negative infinity by looking at our end behavior, and really by plugging in infinity. That'll really help us figure out what's happening in the end behavior of a graph. So let me look at a very complicated looking equation. Let's do another one. For example, the limit x approaches infinity of 3x cubed minus 7x to the 4th power minus 2x plus 1. What is this going to be? What's this going to be? we're going to use our trick with this, right? We're going to imagine plugging in infinity. Plug in. And we're going to get 3 times infinity squared, cubed, minus 7 times infinity to the 4th power. Whoa. Infinity to the 4th power, minus 2 times infinity plus 1. We're going to imagine plugging in, right? That's infinity here. Infinity to the 4th power. Imagine plugging in, right? Get better at writing infinity, everybody. You're going to get so much infinity practice here. Oop, that's kind of okay. So we got a lot of infinities. How do we know which one is the best? How do we know which one is like the most important? How do we deal with these cube squares, all these other infinities? Like I got a positive here, but I got a negative here. Like how do we balance the infinities out, right? Which one has more influence? And there's really easy solution. Easy way to solve this. This positive 1, I said that was insignificant, right? 1 is not going to change my answer. So I can really ignore the 1. Too small. The positive 1, don't care about. It's not going to change anything about my answer. But all 3 of these have infinities. Which one is the most important? Well, clearly, my 3rd power and my 4th power are going to be the ones that have the most influence, right? Those are bigger exponents. So this infinity here that's by itself, this I can also ignore. Too small. Too small. It's not got a power. Its power is it's only infinity to the power of 1. Infinity to the power of 1 is way smaller than infinity to the power of 4. And in fact, this infinity cubed is also much smaller than infinity to the 4th power, so I can ignore this one. So only this one matters. And in using these infinities, only the biggest exponent counts. Only the biggest exponent matters. You only need to pay attention to the infinity that has the highest power. It is the biggest, it's the boss infinity, it's the biggest infinity there is. So only the exponent that is the largest infinity matters. So now we've crossed out all the other non-important pieces. What's the answer for this one going to be? I have -7 infinity to the 4th power. Am I going to go positive infinity? Is this going to end up in a positive direction? Or is this going to end up in a negative direction? There you go. Negative here, -7. Doesn't matter, the 7 is, again, too small, it doesn't matter. But the negative sign counts, so we're going to go towards negative infinity. That's what this infinity limit's going to be. So only the biggest exponent matters. You can ignore everything else. Really simplifies your problem. And because it was -7, infinity to the 4th power, that means our infinity is going to be negative. All right, let's try one more. Whoopsies. Limit, example, as x approaches this time negative infinity of x plus 2x squared minus 3x cubed plus 4x to the 5th power. What's this going to be? Positive infinity or negative infinity? Write this a little bit better. The limit as x approaches infinity of that equation there. Well, clearly, the only one that matters is this fifth power. This is the only one that matters. That doesn't matter, that doesn't matter, that doesn't matter. I can cross all those out. So now we have to figure out, are we going to have a positive or a negative infinity left over from this one here? Bryce says positive, Jessica says negative. Why positive, Parisa? Maybe we'll have you explain. You want to argue your case? I didn't pay attention to the limit. Yes. Jessica, you want to explain? Why is it negative? Well, how is this going to be negative? It's a power, right? Just like before when we had squared, negative infinity squared made it positive, right? So shouldn't this make it positive, negative? Go on. Yes, because it's odd, right? Negative odds stay negative, right? Negative fifth power, it goes like it's like tick-tock back and forth. Squared is positive, cubed is back to negative. Fourth power positive, yes. Very good. This will be negative infinity, everybody. Negative infinity because fifth power, odd power, stays negative. Right? Negative fifth power keeps us negative. Very good. All right. So that's how you can figure out infinities, how you can figure out negative and positive infinities. But we need to also figure out, what about asymptotes? What about horizontal asymptotes? How do we figure out if a function, how can we tell if a function is approaching a horizontal asymptote? And how do we find that asymptote? Horizontal asymptotes. How do we figure out about these horizontal asymptotes? Where do these come from? For horizontal asymptotes, the only kinds of functions with horizontal asymptotes, functions with horizontal asymptotes, there's only like a few kinds. First, you have your exponential functions. Exponential. That's like 2 to the power of x, or e to the negative x. Exponential functions, they have horizontal asymptotes, usually only in one direction. Only in one side. Usually only one side of that function has a horizontal, right? Because they look like this, and so the only horizontal asymptote is this direction, right? So they have a horizontal asymptote on one side and infinity or negative infinity on the other. So exponential functions have horizontal asymptotes. Or you have rational functions. That's where you have a function like something divided by something else, like x plus 2 divided by x minus 7. They're functions that look like this. They have horizontal asymptotes located here. They also have vertical asymptotes, but they have horizontal ones as well. Rational functions are one of the few that have horizontal asymptotes. ln, there was a question about ln. like natural log or log functions, they do not have horizontal asymptotes, they have vertical asymptotes. Vertical asymptote, but this goes on to infinity. ln only has a vertical asymptote, no horizontal asymptote. So the only ones that we need to concern ourselves with horizontal asymptotes are exponential equations and rational functions. And solving these, if you know the tricks, again, you know these tricks, are really easy when you think about how to do them. If you know the tricks, I'm going to show you the tricks. Once you know these tricks, you can do these questions no problem. So let's start with rational functions. They're probably the easiest ones to do. For example, find the limit as x approaches infinity of 3x plus 1 divided by 2x minus 5. Find the horizontal asymptote. I'm going to abbreviate it H because I'm lazy. Horizontal asymptote. VA vertical asymptote, HA horizontal asymptote. SA is a skew asymptote. We'll get to that maybe. No. Horizontal, vertical, these are the ones we need to worry about. Rational functions. This is x plus 2. It doesn't really matter. This is x plus 2 over x minus 7. X plus 2 over x minus 7. So we have this limit here. Where is the horizontal asymptote of this equation, 3x plus 1 over 2x minus 5? Where is the horizontal asymptote? And what is the answer to this question of the limit as x approaches infinity of this number here? Like before, what we're going to do is use our trick of plugging in. We're going to plug in, plug, goodness gracious. I'm going to plug in infinity. So we're going to get 3 times infinity plus 1 over 2 times infinity minus 5. Right? And again, the only thing we're going to care about is the biggest exponent of the top part and the biggest exponent of the bottom part. So this 1 doesn't matter, and this 5 doesn't matter. Only look at the biggest exponent. We only care about the highest exponent. In this case, they're both a 1. And so we have 3 times infinity divided by 2 times infinity. Those are the only, right? This is the only part that matters. This part right here. 3 times infinity divided by 2 times infinity. Well, what I can do now, I can think about, well, I have infinity on the top and infinity on the bottom. So I can basically infinities. I have, right, it's like a variable. I can cancel the infinity here, cancel the infinity here. So what's my answer? 3 over 2. That is the horizontal asymptote for this function here. 3 divided by 2. I took my infinities. I looked at only the biggest infinity, only the biggest. I canceled them out because there's like 3 infinities up here, 2 infinities down here. Cancel it like a variable. And I just have 3 divided by 2. That's my answer. That is the horizontal asymptote. If I were to graph this equation, I were to graph this function here, it would have at 3 halves, which is like between 1 and 1.5, right? Right at 3 over 2, that's at 3 halves equals y equals 3 halves. That's going to be where this function has its break at 3 halves. That's the level where this function is going to have its break. The vertical asymptote, where is that going to be? Where's the vertical asymptote going to be? Remember, the vertical asymptote is the bottom. That's going to be here, which is going to be 5 over 2. Right? Because that would make it 0. If you said 2x minus 5 equals 0, imagine solving that. Add the 5 to both sides, divide by 2, you get 5 halves for a vertical asymptote. The vertical asymptote stays the same, it's just the bottom part. But your horizontal asymptote, plug in the infinities and cancel them out. Horizontal asymptote at y equals 3 halves. And that's the answer for the limit, right? That horizontal asymptote is the limit that we're trying to find. Should we try another? Oop. What is the limit? This time, x approaches negative infinity of x squared minus 3x cubed plus 2 over x cubed plus 1. Manual, that hurting is called learning. That's that feeling, just the juices flowing. The spice must flow. If anyone likes Dune. Anyway, here's our next function. Spicy. Alright, anyway, here's our function, x squared minus 3x cubed plus 2 over x cubed plus 1. What is the horizontal asymptote of this equation? What do we care about? Immediately, the first thing you should do, cancel everything except the biggest exponent. I don't care about squared, I don't care about 2, I don't care about 1. The cubes are the only ones that matter. That's our biggest one in this situation. The only ones that matter are the cubes. Okay. So now I imagine plugging in negative infinity. So what's this going to be? If I imagine this is negative 3 times negative infinity cubed over negative infinity cubed. What do I have here? Again, I have negative infinities, and just like my positive infinity, I can cancel these. I have 3 infinities on the top, 3 negative infinities on the bottom. They can cancel. So what's my limit? Only thing left, this is a 1 on the bottom down here, so really it's just negative 3. Okay. So you're looking at your positive, negative infinities, seeing how they cancel, only caring about the biggest exponent. And again, your horizontal asymptote, the line of this graph is going to be where this horizontal asymptote ends up, negative 3. This graph is going to have this horizontal line at negative 3. That's going to be where the graph sweeps around. All right, what if, oh god, this is all great, but what if the exponents don't match? For example, if I had, as x approaches infinity, let's say I have 2x squared minus 5 over x plus 1. X squared minus 5 over x plus 1. What if my exponents don't match? Where is this going to go? Again, the only thing that matters is the biggest exponents. So I'm going to ignore the 5, and I'm going to ignore the 1. And then my biggest exponent on top is 2x. My biggest exponent on bottom is just the x by itself, 2x squared. So these are the only ones that matter. And just like before, when I canceled, I can cancel x's, or infinities. I can cancel my variables here. So I have 1x on the top, 1x on the bottom, and 2x's on the top. So one of my x's will cancel here. The entire x will cancel here. Cancel x's. And what I've got is 2x. The limit as x approaches infinity of 2x. Well, I can do that. We plug our infinity in. And if I plug my infinity into 2x, where's it going to go? 2 times infinity? Well, that's going to be infinity. This equation does not have a horizontal asymptote. No horizontal asymptote, because it does not go to a specific number. At the top value, the top is bigger. And so if I'm going to infinity and my top number shoots off to infinity, there is no asymptote. It doesn't reach a particular number. It's going forever. Top value goes to infinity. I'm never going to reach a particular asymptote. It's going to go forever. And I figured that out by looking at my functions, by looking at my variables, my biggest variable on the top, biggest on the bottom. I saw which one was left over, which one had a leftover variable. And the top value had a leftover x, right? This was like over 1, right? My top one had more x's. Since the more x's, it got the infinity, and if I go infinity forever on the top, it's going to go forever infinity, so I have no horizontal asymptote. It's going to go forever. What if, whoopsies, it was the other way around? What if instead, limit as x approaches infinity of x plus 1 over 3x cubed minus 7x? What if my bigger one's on the bottom? What is that like? Jessica, you're asking, every time the top is bigger, there is no horizontal asymptote. That is correct. Every time the top is bigger, there is no horizontal asymptote. What if the bottom is bigger? Well, again, here, the only ones I care about are the biggest exponents. So 1 doesn't matter. This x doesn't matter because I have a cube. So the only ones are these two here. And again, I cancel my x's. This x is going to go away. One of these is going to go away, leaving 2 x's left over. So I really have 1 over 3x squared. That's really what I have at infinity. Right? So now my bottom is bigger. And I have like 1 over infinity. Well, if I take a a fraction, 1 divided by a really, really, really big number, 1 divided by a million, it gets smaller and smaller. This becomes becomes really small. Becomes small. And so small, in fact, that it reaches 0. 1 divided by infinity is equal to 0. If you have infinity on the bottom, your answer is 0. Anything divided by infinity becomes a 0. Becomes so small that we make it into a 0. So anytime the top is bigger, you get infinity for your answer. Anytime the bottom is bigger, you get a 0 for your answer. And that's the difference if you have, doesn't matter how much bigger, right? This was a squared. Doesn't matter how much bigger. If this was squared down here, it's still infinity. Infinity squared is still infinity. If the bottom is bigger at all, right? No matter how many exponent bigger, it's still going to be 0. If the top is how much bigger, it's still infinity. Top is bigger, you have infinity. Bottom is 0. Oh, there is, actually, I should mark this. There is a, why is this freaking out? Hold on, everybody. I don't know what's happening here. Fine. This does have your horizontal asymptote is y equals 0. Because it's a number, you have a horizontal asymptote for this one. You do have a horizontal asymptote when you get a number for an answer. It's just your horizontal asymptote is 0. Is y equals 0. Okay? So these are the kinds of situations you're going to face. Right, let me zoom out a little bit. These are the kind of situations you'll see. You'll have equations. Equations where you plug in your infinity, your negative or positive infinity, figure out where your graph is going, your end behavior. What is the end behavior of these graphs? You'll have your vertical and horizontal asymptotes, your rational functions, where you plug in your infinity and you figure out, well, which one's bigger, which one's smaller. If they're the same, they cancel out, you're left with the fraction. Or if they're negative or positive, be careful about your fractions. If the top is bigger, you don't have a horizontal asymptote, it goes forever. But if your bottom is bigger, your horizontal asymptote is at 0. 1 divided by infinity always becomes a 0. All right, everybody? So, with that said, I think we're out of time. Yes, we're definitely out of time. I want to mention that your assignment, let me show you what your assignment is, everyone. I'm going to keep these notes, upload them to Schoology. Oh, this is the wrong class. Your assignment is a worksheet that I have posted to Schoology. Right here. Limits at infinity. Try that worksheet. Oop, it says due the 6th. That's not correct. It is due next time we meet on Thursday, the 8th. Work on this handout. Limits at infinity. There are, I don't remember how many questions. Half multiple choice, half free response. So try this out, everybody. Do your best. We'll go. That's it for me. Yes, you can say goodbye. Once you say goodbye, you're free to go. I'll see you all next time.